Hello, everybody. We're at the culmination of our discussion of the interstellar medium, and it is a perfect transition because the end of the ISM is the beginning of our star formation. That is going to be the subject of the next topic we go into in the class. But let's go ahead and take a look at Dr. Lindsay's favorite part of the ISM, the molecular clouds. And I like these for a variety of reasons. One, they are stunning to look at. So I know I've shown this in a previous video, but let's just take a minute to enjoy the grandeur of what's called the Mystic Mountain in the Carina Nebula and talk a little bit about what we're seeing. So you can see the general ISM surrounding this very, very clearly distinct part of the ISM that looks like a cloud in outer space, a very colorful cloud with lots of detail, but it still looks like a cloud. What is the primary difference between this phase of the ISM and the other phases of the ISM? The temperature is cold enough to form molecules. So it is in these molecular clouds that we get our coldest temperatures, our densest regions, and we turn away from just talking about atoms to actually forming molecules. And then that rich diversity of molecular stuff that I talked about in the ISM, all the different molecules we see, this is where they are. And since everything's so dense, this is the regions where we set up the scenario to actually get these clouds to collapse to form new stars, or at least small sections of these clouds. So anytime I'm going to be talking about star formation, picture these as your starting point. And this has enough material to form dozens upon dozens to hundreds, and sometimes, depending on the cloud, thousands of stars. There's a star being born right here. All right, so the molecular clouds, our last phase is the ISM that we're going to talk about, where we distinguish the phases of the ISM by what state the hydrogen is in. And here, the hydrogen is molecular. So this would be H with a subscript of a 2, molecular hydrogen, where two hydrogen atoms have molecularly bonded together. So these are the densest regions of the ISM, where they can have densities up to about 1,000,000 particles per cubic meter at the edges, so these thinner regions that you're seeing. And in the very densest parts of these, because there's not the same density everywhere, there are clumps that are higher density, and that's where you get star formation. It's in these denser clumps, you can get up to 10 to the 12th, 1 trillion particles per cubic meter. A trillion. And you might be thinking, wow, that's really dense. But that's still about as dense as a vacuum chamber here on Earth. It's 1 trillionth the density of the air in the room that you're in. The air in the room is about 10 to the 24th particles per cubic meter. So we're not very dense yet. Okay, but it is very, very, very dense for outer space. It's the densest regions in space, and it can get so dense because we're extraordinarily cold. We have temperatures that are 10 to 50 Kelvin. That's getting really close to that zero mark of absolute zero. So these are cold and dense enough for chemistry to happen, and you can form and maintain molecular bonds. All the other spaces in the ISM, there's not high enough density and it's too warm where the molecular bonds will get broken. Either that molecule gets whacked by a particle too hard, which breaks a molecular bond, or a photon comes along and breaks a molecular bond. These molecular clouds are the regions where densities are high enough to shield light from coming in and breaking molecular bonds, and it allows things to cool down enough to actually start driving and forming some pretty complex molecules. And we call these molecular clouds, even though it's really the dust that we're really seeing that makes these amazing visual objects. You have to remember that the dust is only 1% of all of the mass that is there. Most of it is in gas. And in the molecular clouds, most of the gas is molecular hydrogen gas. Two hydrogen atoms molecularly bonded together. So please keep that in mind that the majority of these things are molecular hydrogen gas. It's just you can't really see the molecular hydrogen gas. And yes, these are our stellar nurseries where new stars are going to be born. So whenever we start talking about star formation in the near future, picture these objects like this Horsehead Nebula in your brain. And they come in a variety of sizes. So some molecular clouds are giant that can span hundreds of parsecs across. Some span tens of parsecs across, like our Mystic Mountain right here. And some are only a few parsecs across, like we can see up here. So these molecular clouds that we're seeing in this top image, they actually look like little tiny clouds that are floating. The background is the Carina Nebula, and you can see that it has general hydrogen alpha emission going on there. You can see these dark nebulae, these molecular clouds that are only a few parsecs across. And these isolated ones that are in these really intense environments where you have like an emission nebula, we call these Bach globules, these sort of small, few parsec size molecular clouds, where there's enough material there to form only a few stars. And they can form stars, but it is a race against time in the environment because these are in environments where a lot of other stars have already formed, which means that there are a couple of O and B type stars, super high temperature, emitting lots of ionizing ultraviolet radiation, which will erode these things from outside in, literally blow them away. So you have to, if you're gonna, if these Bach globules are going to form stars, they better do it in a hurry before they just get evaporated away and just become part of a less dense, ionized part of the interstellar medium. So as we've already mentioned, we have the dark nebulae like these are often called, these are molecular clouds. But one of the really cool things are is when the very large ones, what we call giant molecular clouds, the ones that are dozens to hundreds of parsecs in size, is these regions become these intense regions of star formation. They make these really incredible things for us to look at. And if you want to talk about where new stars are going to be born, you're talking about making hundreds to thousands of stars out of giant molecular clouds. Before I talk about giant molecular clouds, I do want to talk about what molecules are there. Just a quick sort of review with a little bit of addition. Over on the right is just a highlight of some of the most abundant molecules we find. Again, the most abundant of all of them is molecular hydrogen. But let's talk about the molecular clouds and why we can actually get molecules forming in them. It's because that these are the densest regions of the ISM. The density of the molecular clouds is a shield that protects the molecules. So you have this dense cloud. These are usually going to be surrounded by things like O and B type stars, which are giving off lots of ultraviolet radiation. But that ultraviolet radiation will hit the dense boundaries of these clouds and get absorbed, either by breaking apart molecules or just absorbed by the dust. And whenever it actually encounters, say, a molecule on the outskirts of these molecular clouds, the ultraviolet light has more energy than the molecular bond holding together. So that molecular bond will break. And whenever we have an ultraviolet or really any light that breaks apart a molecule, we call that photodissociation. So we will dissociate, we will break a molecule by a photon, photodissociate it. And that is happening on the boundaries of this, which means that all the ultraviolet radiation can never penetrate to the interior regions of the cloud, allowing it to get super duper cold, reach temperatures of 10 Kelvin or so. And at those temperatures, you can really start driving some advanced, some pretty complex chemistry, as shown by the range of molecules shown there and that I had in a previous video. And where's most of this chemistry happening? It's happening on those precious surfaces of dust grains, where you can get the atoms close enough together to really drive this chemistry to create all of these amazing molecules. So even though we talk about all the awesome molecules that are in molecular clouds, and we're about to realize that the large number of all of these, especially molecules like formaldehyde and carbon monoxide, uh, even though all of this rich uh, amount of molecules are there, please don't forget that molecular clouds are almost entirely made out of molecular hydrogen. That's 99% of the mass of these things. So please remember that these are made out of molecular hydrogen. And let's take a look at some giant molecular clouds. We've looked at this before. Here's the Orion molecular cloud complex that spans hundreds of parsecs. It's absolutely enormous. And whenever they get that large to the 50 to 100 or larger parsec size in diameter, we call these things giant molecular clouds. They are the largest objects of the ISM. And even though they're the largest objects of the ISM, they don't take up a whole lot of volume because they're really dense compared to the rest of the ISM. It's only 1% of the total volume of the ISM. However, most of the mass of the ISM, a significant amount of the mass of the ISM, is located in these giant molecular clouds. In fact, the giant molecular clouds within the Milky Way galaxy contain enough material to form hundreds of thousands of suns. So these giant molecular clouds really can produce a large number of new stars. But we still haven't talked about how we really go about observing and characterizing these. How do we know the temperatures? How do we know the densities? Sure, we can just look and see things like the Bach globules and the Mystic Mountain, but that's just seeing them. How do we actually characterize them? How do we go about doing all the observations so we can map out where all the molecular hydrogen is and tell all the fun details, like how much molecular hydrogen is there? What is the temperature? What is the density? And for that, we have to go back to understanding how molecules absorb and emit light, molecular spectroscopy, which was more complicated than how atoms absorb and emit light. Atoms, we only had the electrons that we could move around through the energy levels. We had our electron energy transitions. But molecules also had rotational, you could rotate the molecule around and around and around. And we could vibrate the molecular bond, play the molecule like an accordion or stretch it in weird sorts of ways. So molecules had additional spectral lines due to vibrations and rotations. And if you remember, those rotations happened at radio wavelengths. So rotating a molecule happened at radio wavelengths. Radio wavelengths, being long wavelength radiation, can penetrate through the dust, can see through the dust. So this seems like an opportune part of the electromagnetic spectrum to start looking for these molecules, because it's these rotational radio wave transitions that they don't care if they're in this dense cloud of gas and dust. That radio wave will go straight through it and out of the cloud and dust so we can detect it here on Earth. We only have one major problem though. One, we're dealing with molecular hydrogen. Well, that's actually the problem. The majority of these molecular clouds are molecular hydrogen. However, molecular hydrogen poses some significant problems. One, as a molecule, now it has 2 protons and 2 electrons, no more 21 centimeter radiation. You can't play that parallel anti-parallel game. So molecular hydrogen doesn't have 21 centimeter radiation. Can't use that to find molecular hydrogen. Also, just by the nature of the molecular hydrogen, the molecule, it doesn't really have any significant spectral lines. It's not very good at absorbing and emitting light. And if it's not giving out spectral lines, how are we going to go about seeing it? And the trick is, since it doesn't really interact with light very easily, it doesn't have a whole lot of easy to find bright spectral lines. What we have to do is we have to infer its existence, because the molecular hydrogen hangs out in a molecular cloud where there are other molecules. So what we'll do is we will look for rotational radio spectral lines due to other molecules. And if we see those, then we can infer that molecular hydrogen is there just because there is a lot of molecular hydrogen. It is the majority, the vast majority of the mass of a molecular cloud. So we call these other molecules that we'll look for that indicate that we're looking at a molecular cloud full of molecular hydrogen tracer molecules, because they allow us to trace out the densities and the densities and the pressures and the temperatures of these molecular clouds. They also allow us, they act as a tracer to point out where the H2 is. You have more tracer molecules, you have more H2 molecules. So the most common tracer molecules, the easiest ones for us to observe, are carbon monoxide, ammonia, and formaldehyde. Although you can use pretty much any of the molecules that exist in molecular clouds. So other popular tracers that people use, water, hydrogen cyanide, methyl alcohol, and the 150 or so, now it's pushing closer to 200 others. And I want to just show you how this would work. So let's go back to our Trifid nebula, where we have our emission nebula, we have a reflection nebula, and here we have our molecular clouds seen as these dark dust lanes. And we want to go ahead and trace out where the molecular cloud part is. So we take a spectrum from in these various regions where the arrows point, and we look for a tracer molecule. So we'll look for something like formaldehyde. And that's what this line right here, this absorption line, is formaldehyde. And we'll just see how much formaldehyde is there. Very weak formaldehyde feature here, not very much. There's some here. As you can see, it looks like there's a little bit of a cloud there. By the time we're in the dust lane that we can visually see, there's a lot. So we found the molecular cloud, and then there's some here. So it's allowing us to trace out the amount of formaldehyde that's there, and then we can translate, because we know how chemistry works. So if you're going to form this much formaldehyde, that translates to this much of molecular hydrogen, and we have figured out and traced out the molecular cloud. So we use tracer molecules to detect and characterize molecular clouds. All right, that's it for the ISM. Next, we start forming stars, and I can't wait to get there. It's super fun and exciting stuff.